Welcome to the session on linear programming problem, formulation and graphical solution. The contents are components of linear programming problem, formulation of LPP, the general linear programming problem, convex sets, convex functions, graphical solution, exceptional cases, which are alternative optima, unbounded solution, infeasible solution followed by the references. Definition of linear programming problem. LPP is a technique to determine an optimum schedule of interdependent activities taking into account the availability of the resources. The word programming is used to mean a process or a way of determining a particular strategy of action from amongst a variety of available alternative courses of action. The word linear indicates that all the relationships involved in that particular problem are linear. The components of LPP are decision variables, which are the activities that compete each other for sharing the available resources in linear programming problem. These variables are assumed to be continuous, controllable, and non-negative. The objective is a clearly identifiable and quantitatively measurable aim. The variables in the objective function of an LPP must be linearly related. For example, the objective of an LPP could be the maximization of the profit, sales or output, or minimization of the loss cost or time. The constraints are the linear inequalities or equalities in terms of the decision variables that represent the limitations on the use of available resources like raw material, manpower, money, storage capacity, etc., that limit the extent to which an objective may be attained. Linear programming problem mathematical formulation. Step 1. Study the given situation to find the key decisions to be made. Identify the variables involved and designate them by symbols xi. State the feasible alternatives, which usually are xi greater than or equal to 0 for all I. Identify the constraints in the problem. Express the constraints as linear inequalities or equations such that the left-hand side is expressed as linear functions of the decision variables. Step 5. Identify the objective function and express it as a linear function of the decision variables. So let us see an example of product allocation problem where a company is producing three items, say A, B and C, which are processed on three different machines M1, M2 and M3, yielding a profit of 2, 3 and 5 rupees respectively. One unit of product A requires 2 minutes each on M1 and M2 and 1 minute on M3. One unit of product B requires 4 minutes on M1 and 3 minutes on M3, while one unit of product C requires 2 minutes on each machine. The daily availability of machines is 4, 2 and 4 hours for A, B and C respectively. Formulate the problem as an LPP to maximize the daily profit, assuming that whatever is produced is consumed in the market. So we will put the data in a tabular form. Machine M1, M2, M3, time required by machine per unit in minutes. So machine A requires 2 minutes on M1, 2 minutes on M2 and 1 minute on M3. Similarly, product B requires 4 minutes on machine M1 and 3 minutes on machine M3, and product C requires 2 minutes on M1, M2 and M3. Now availability in minutes. It is given in hours, so we need to convert it into minutes. Step 1. Key decision to determine the number of units of products A, B and C to be produced on a daily basis. Step 2. Let xi, I going from 1 to 3, denote the number of units of product A, B and C to be produced daily. Step 3. Feasible alternatives. Since we cannot produce negative quantities and the least number of units that can be produced is 0 or nil, therefore the obvious feasible alternatives are that xi is greater than or equal to 0 for all I varying from 1, 2 and 3. Step 4. Identify the constraints. The constraints are on the machine capacities. So machine M1, 2 units of X1 plus 4 units of X2 plus 2 units of X3, maximum availability is 240, so less than or equal to 240. So similarly, machine M2, 2 minutes, 2 times X1 plus 2 times X3 less than or equal to 120. X1 plus 3X2 plus 2X3 less than or equal to 240. So this is your third constraint, machine M3. Objective function is to maximize the profit. Maximize z is equal to 2 times x1 plus 3 times x2 plus 5 times x3, because we are having a product, x1 is having a profit of 2 rupees, x2 is having a profit of 3 rupees, and x3 is having a profit of 5 rupees. So we need to maximize the profit. So finally we will write that the given problem is formulated as an LPP as follows. Maximize Z, which is the objective function. We are trying to maximize the profit subject to the constraints of the availability of the machines, machine M1, machine M2, machine M3, which we have formulated. And then these are the non-negative restrictions. X1 greater than equal to 0, number of units should be positive, greater than equal to 0, greater than equal to 0, since we cannot produce any negative quantities. So this is now the general linear programming problem. Let Z be a linear function defined on n-dimensional real coordinate system. Z is equal to summation Cj xj, where Cj's are constants. Let Aij denote an m cross n real matrix, and let B1, B2, Bm be a set of constants such that summation of Aij is either greater than equal to, less than equal to, or equal to Bi for all I going from 1 to m. Like you can consider this example. Maximize Z is equal to summation Cj xj. So j is 1, 2, 3. Cj is a cost function, 2, 3, 5. Xi is xj's. Subject to the constraints, so 2 times x1 plus 4 times x2. So this is my constraint, C11 x1 plus, so here we have Aij. Here we have summation Aij is less than equal to, greater than equal to, or equal to Pi. And let xj greater than equal to 0. These are the non-negative restrictions. The problem of determining an n-tuple x1, x2, xn that makes z, which is the objective function, a minimum or maximum depending on the problem, and satisfies b and c. This is the set of constraints b, and the set of alternatives, feasible alternative c, is called the general linear programming problem. The linear function z equal to summation Cj xj, which is to be minimized or maximized, is called the objective function of the general linear programming problem. The set of inequations in B are called the constraints of the general linear programming problem. The set of inequations in C are called the set of non-negative restrictions of the general linear programming problem. An n-tuple x1, x2, xn of real numbers which satisfies the constraints of a general linear programming problem is called a solution to the general linear programming problem. Any solution to a general linear programming problem which also satisfies the non-negative restrictions of the problem, xi greater than equal to 0, is called a feasible solution to the general LPP. Any feasible solution which optimizes the objective function of a general linear programming problem is called an optimum solution to the general LPP. It is also called as optimal, so depending upon whatever term you want to use. Convex sets. A subset S contained in Rn and dimensional real coordinate space is said to be convex if for any 2 points x1 and x2 in S, the line segment joining the points x1 and x2 is also contained in S. In other words, a subset S contained in Rn is convex if and only if implies and is implied by x1 x2 belongs to S implies that lambda x1 plus 1 minus lambda x2 belongs to S for lambda lying from 0 less than equal to lambda less than equal to 1, both inclusive. So this implies this both ways. So let us consider a few examples of convex sets in two-dimensional real coordinate space. So this is a square. So if I take any 2 points x1 and x2, so the line segment joining x1 and x2 is contained in this S. Similarly, ellipse, any 2 points, we can have a pentagon, a triangle. So these are examples of convex sets in R square. Let us look up this example for ring, this figure, all these examples. If I take any 2 points, say x1 and x2, and join them, so this area, this part of the line is outside this set S. This is my set S. So all these are examples of non-convex sets in R square. Definition of an extreme point or a vertex is that an extreme point of a convex set is a point of the set which does not lie on any segment joining to other points of the sets. A point of a convex set S is an extreme point of the set if there does not exist any pair of points x1, x2 belonging to S such that x can be expressed as lambda x1 plus 1 minus lambda x2, where 0 is less than lambda is less than 1. So we have a strict inequality here. An extreme point is a boundary point of the set, not necessarily vice versa. That means not all boundary points of a convex set are necessarily extreme points. Given a set of vectors x1, x2, xk, a linear combination x equal to lambda 1 x1 plus lambda 2 x2 so on plus lambda k xk is called a convex combination of the given vectors if lambda I is greater than or equal to 0 and summation lambda I equals unity. The set of all convex combinations of a finite number of linearly independent vectors is called a convex polyhedron. A simplex in n dimension is a convex polyhedron having exactly n plus 1 vertices. In 0 dimensions, it is a point. In 1 dimension, it is a line segment. In 2 dimensions, it's a triangle. In 4 dimensions, it's a tetrahedron, and so on. Theorem: the set of all feasible solutions to the linear programming problem is a convex set. We need to show that every convex combination of any two feasible solutions is also a feasible solution. The theorem is trivially true if the set of solutions has only one element. Let us assume that there are at least two solutions, say x1 and x2. We have ax1 equal to b and ax2 equal to b for both x1 and x2 greater than or equal to 0. For lambda lying from 0 to 1, 0 less than or equal to lambda less than or equal to 1, let x be expressed as lambda x1 plus 1 minus lambda x2 be any convex combination of x1 and x2. Note that all the elements of the vector x are greater than or equal to 0. Let us now consider ax. A as it is, x this that we've taken, and then we'll open the brackets. A lambda x1, so lambda is outside, ax1 is b from here. Similarly, 1 minus, and we've opened up the bracket, lambda multiplied by x2, so ax2 is b again. So this gets cancelled, we are left with b, that is ax is equal to b. Hence the set S such that, equal to x such that x is a feasible solution to an LPP is a convex set. There is another result which we use in trying to obtain a solution. The objective function summation cjxj assumes its minimum or maximum at an extreme point of the convex set K generated by the set of feasible solutions to the linear programming problem. If it assumes its minimum or maximum at more than one extreme point, then it takes on the same value for every convex combination of those particular points. So the proof can be seen from Hadley. This is given in the references. LPP graphical solution. Step 1. Formulate the given problem mathematically as an LPP. Step 2. Plot a graph representing all the constraints of the problem as equations and identify the feasible region or the solution space. The intersection of all the regions represented by the constraints of the problem lying in the first quadrant gives the feasible region. The feasible region obtained may be bounded or unbounded. Obtain the coordinates of the corner points of the feasible region. Step 4. Compute the value of the objective function at each corner point. Step 5. The optimum feasible region is obtained at that corner point that optimizes, that is maximizes or minimizes depending upon the problem, the value of the objective function. So why do we need to concentrate on the first quadrant only? This is because of the feasible alternatives or non-negative restrictions that we have xi greater than or equal to 0 for all I. So this is an example. Maximize z is x1 plus 8x2 subject to the constraint x1 plus x2 less than or equal to 6, 4x1 plus 2x2 greater than or equal to 4, x1 x2 greater than or equal to 0. So for graphical solution we can have only for two variables, two decision variables only, because we have two axes x1 and x2. So we can solve only two decision variable problems graphically. First, we will plot these two lines by treating the inequations as equations. So first I will take x1 plus x2 equal to 6 and then find the coordinates. So I'll take x1 is 0, At this point x2 is 6 and similarly this. So these 2 points will help me in drawing my line. Similarly x1 and x2, when x1 is 0, x2 is 2. So I'll plot these lines on a graph. So this is my line, x1 plus x2 is equal to 6 and 4x1 plus 2x2 is equal to 4. Now the constraints are x1 plus x2 is less than equal to 6. So I will concentrate on this region below this line, and 4x1 plus 2x2 is less than equal to 4. So I will is greater than equal to 4. So you can look up here. So this is less than equal to 6. This is greater than equal to 4. So less than equal to 6 and greater than equal to 4. So this is the region which is the feasible region where I'll find my solution. So I'll look up the extreme points only, extreme vertices of this shaded region which is my feasible region. So the extreme points are A, B, C and D. The coordinates are 1, 0, 6, 0, 0, 6 and 0, 2. I'll make a table where I'll put the extreme points, then I'll put the values of the coordinates x1, x2, and then I will compute the value of the objective function which is x1 plus 8 times x2 at these values of the vertices. A10, that means only 1, 6 times x1 plus 0 is 6, 0, 6, 8, 6 are 48 and D is 0 to 16. So since I need to maximize my objective function, my maximum is 48. Z is 48 coming at this point. C is equal to 0, 6. That means I need to manufacture 0 units of x1 and 6 units of x2 in order to maximize my profit at 48 rupees if the problem is mentioned in rupees, otherwise units. So optimum solution is x1 is 0, x2 is 6 and maximum Z is 48. So this is my x1 axis, this is my x2 axis, and it is immaterial whether you plot x1 here or you plot x2 here, that hardly matters, but you need to be particular about your coordinates. So let us move to another example. So x1 plus 4x2 subject to these. So I'll plot my lines treating the inequations as equations and find the vertices. So 0, 18, 0, 3, 0, 10 and so on. So now greater than equal to 18, greater than equal to 12, greater than equal to 10. So let us move this. So here I have made this on a graph paper. So x1 axis, x2 axis, and I have plotted my 3 lines. x1 plus 4x2 greater than equal to 12, so above this line, entirely above this line. And then 2x1 plus x2 equal to 10 above this line, again above, entirely above this line and above this line. So this region is the feasible region as it satisfies all the 3 constraints simultaneously. If I include this region, then what will happen? This constraint is not being satisfied because this area below this line is less than this. So all the shaded region will form my feasible region. On x1 axis, 1 square is equal to 2 units. On x2 axis, 1 square equals 2 units. So again, I'll make a table, extreme points A, B, C, D, coordinates, and my values of the objective function. Again, I need to minimize Z. So optimum solution to the given LPP is x1 is equal to 2, x2 is equal to 6 units, and minimum value of the objective function is 14. Now let's move on to exceptional cases, alternative optima. Solve the problem graphically. Minimize Z is equal to 4, x1 plus 2, x2, subject to the constraints. So same constraints which I had taken earlier. So here again the same feasible region greater than equal to, this is the same as the earlier problem. The only difference is now you will see what the difference is. It is in the objective function I have changed here. So extreme points are A, B, C, D, vertices, coordinates of the vertices, and then value of the objective function. Now what we observe here is we want to minimize, let us look at minimize the objective function. So here I'm getting minimum 20 and minimum 20 at 2 points B and C. So let us look up B and C. So at B as well as on C, I'm getting 20. So this is the case of alternative optima. So 4 units of x1, 2 units of x2 is giving me minimum z equal to 20, and so is 2 units of x1 and 6 units of x2, that is also yielding a minimum profit of 20. What I observe here is there is an infinity of solutions. Why? Because on the line BC I can take any other point. Let us take this point where x1 is 3 and x2 is 4. Then also if you will compute, you will get minimum z is 20, and you can take any point on this line segment. So there exists an infinity of solutions. Any point on the line segment BC gives the minimum value z equal to 20. So why is this happening? This is happening why? Because if you will observe carefully, I have formulated the problem that I have changed the objective function 4x1 plus 2x2. So if the objective function is parallel to any of the binding constraint, then alternative optima will exist, and we will have a multiple solutions, infinite number of solutions. So 4x1 plus 2x2 is parallel to this constraint 2x1 plus x2. So 2 times this constraint is equal to the objective function. So whenever your objective function is parallel to any of the binding constraints, you will have the case of alternative optima. So let's move to exceptional cases, unbounded solution. So solve the problem graphically. Again, I have taken the same problem as last to last problem, that is example 3. So these coordinates we have already found. This is the graph. Now the case is we are trying to maximize the profit. So if I'll try to maximize, look up here, same graph that we had plotted there. Extreme point A, B, C, D, the coordinates are 12, 0, and then objective is 4x1 plus 2x2. Now if I see the maximum is 48, is coming at the point, the vertex A. So here it is maximum. But this is my entire region. I need to maximize. So you can take up any point. You can take a point here for which x1 is 12, x2 is 18. You can take a point here. You can take a point here. And you will find that your objective function value is improving. It is coming on the higher side. So at x1 is 12, x2 is 0, z is 48, objective function. At 13 and 6 it is 64. At 12 and 18 it is 84. Both x1 and x2 may be made arbitrarily large, and the value of z may be increased indefinitely. Hence the given problem has an unbounded solution. So in case we are maximizing, we can go on increasing the value of z as well as x1 and x2. So this indicates that the problem has not been correctly formulated on the managerial part if we look up that ways. Otherwise, for solving, this is your solution, that this is unbounded solution. Exceptional cases, infeasible solution. Solve the following LPP graphically. So we have found the coordinates by treating them as equations, and we'll plot them on x1 axis and x2 axis. So the constraints are less than equal to 6 and greater than equal to 12. So less than equal to this area and greater than equal to this shaded region. So there is no region which is common to both the constraints. That is, both the constraints cannot be satisfied simultaneously. That means we have infeasible region, and there is no solution, infeasible solution in this case. So such problems will never occur if all the constraints are of the less than equal to type. So no solution to the given problem. There is infeasible solution. These are the references. Thank you.